Hello everyone, Assalamu alaikum. Welcome back for another video in the series. Now it's finally time that we talk about multilayer perceptrons. So what is a multilayer perceptron? Multilayer perceptrons are fully connected feed-forward neural networks with one or more hidden layers. So what does the fully connected mean here? So fully connected means that if you have a given layer, each unit in that layer is connected to all the other units in the next layer. It's actually similar to logistic regression. So in the logistic regression context, we also had everything in the input layer being connected to the next layer. Or if we had multiple inputs, if we had multiple outputs, we had also this setup. And this is actually similar to the multi-layer perceptron, except that in softmax regression, we had an input and an output layer, only no hidden layer. So the main difference between a multi-layer perceptron and softmax regression is that we have a hidden layer now. Also, we use a learning algorithm called backpropagation, which is actually just gradient descent using the chain rule. It's essentially very similar to what we have done in the previous videos when we talked about softmax regression, except again that we now have a hidden layer. Alright, so another term here is the feed forward. So feed forward refers to the fact that we are going into one direction from left to right, essentially from the input to the output. So that means a feed forward. Later, we will see other networks that are not feed forward. For example, there are recurrent networks where we have a recurrent layer where you go essentially backwards as a time dimension. I should also say not all networks are fully connected. So in later videos, we will also see convolutional neural networks which are not fully connected. So here I'm just showing you a multi-layer perceptron with two hidden layers. So we have on the left hand side the input layer, the hidden layer, another hidden layer, and then the output layer. And because we only have one output unit similar to logistic regression and different from softmax regression, this one would be a binary classification problem. And so for the output, we can actually use a sigmoid function similar to logistic regression. Other than that, there's nothing really new here. I mean, this is just like softmax regression, except that we have now these hidden layers. So in that way, there's actually not that much to explain because we have also the same way these weights connecting each unit between the layers, and then and when we compute the partial derivatives for training this network, we can also use the chain rule, the multivariable chain rule that we talked about before. So for instance, if we would want to compute the partial derivative of this loss function on the loss here with respect to one of the weights, that we would also use the chain rule to go backwards, and then the multivariable chain rule to combine the output from different units. So what I mean is, if you have the output here, then we go backwards. So we are interested in this weight W11, just as an example. So there's one part that goes here, you can see it here, and the other part is this one. What I'm showing you is this one here at the top, and then in here for the multivariable chain rule, this is this path here. So there are two paths actually, and that is actually it. That's how we train or update this weight. Notice that there are of course multiple weights and actually multiple weight layers. So here we have, for example, the weight in the second layer. We will train those also, of course. So in this case, the rule would be a little bit different. Here, really what I wanted to say is there's nothing really new here. Now here's a figure we looked at in the earlier video, these different types of learning algorithms, and this algorithm that we use for training the weights and the multi-layer perceptron that I just showed you based on partial derivatives on gradients. That's called backpropagation. That's one type of learning, and yet it remains still to as the most precise learning algorithm. So there was this paper in 2020 where the authors proposed an alternative algorithm that may be similar to what's going on in the brain, but the backpropagation algorithm is still the most efficient one for training neural networks. Now let's talk a little bit about the nomenclature. So here that's the same figure as before, and notice that I'm using these round brackets or parentheses here. So the round parentheses refer to the hidden layer index. So here we have two hidden layers. You can see this is the first hidden layer, and then here we have the second hidden layer. And I could also, instead of writing output here, I could also write activation with parentheses here, uh, because the way the output is computed, if we use the sigmoid function, is it's the same in the same way as these activations are computed. So for example, if you have one activation here, let's say the one in the first hidden layer, this is really computed as the activation based on, let's say, some net input z, where z is computed as the net input. So I'm not showing the biases, so there should also be a bias for each activation. But now if we take a look at this one, so for this one we would compute it the same way, except that z is now not, of course, involving the input access directly. It's based on the previous layer activation. So in this case, you can think of it as the previous layer activations. So here was just focusing on what the inputs are for this one, this on second one here. We have the activations of the previous layer which act as the input to that layer, if that makes sense. So for this layer we have the axes as inputs, and for this layer, the second layer, we have the activations from the previous layer's input. Actually, the main point here also is, I want you to make, is that how we count the layers. So it's quite common. I've seen that a couple of times, referring to the input layer as the first layer in the network. Then the first hidden layer is the second, is a layer number 2. The second hidden layer is the layer number 3, and the output layer would be the layer number 4. We could do that, but then it would be a little bit weird when we talk about logistic regression, because then logistic regression is a two-layer network, which is kind of weird because usually you think, or we think of logistic regression as a single layer neural network. So what I mean is, if we count like that, if we then remove these hidden layers, we have an input layer and an output layer, like in the logistic regression. This would be a two-layer network. And that is a little bit weird. So in this way, we usually use the indices a little bit differently. So this is like the input layer, sometimes also called the zero layer or just the input layer. And the first hidden layer is the first layer, the second hidden layer is the second layer, and the output layer is in this case would be the third layer. So that's a little bit more intuitive if you think of logistic regression as a single layer neural network. Now, like I said, we can use the sigmoid, the logistic sigmoid function here everywhere as activation function. So then it would be really like logistic regression, except that we have these hidden layers in between. But the loss function could also be negative log likelihood that we talked about, or we can also call it binary cross entropy, which is here equivalent to negative log likelihood. Actually, for classification in neural networks, that's also the most common loss function. And also, like in softmax regression, if you have multiple output units, instead of using sigmoid functions here, we can use the softmax function. But I don't have to explain how softmax works again. You can watch a previous video. If you forgot how softmax works, then we have a video for that. You can revisit that, and I'll include this link in the description. Now, an interesting question is this really deep learning? I mean, multi-layer perceptrons have been around, I would say, for 50 years approximately. So, can we really call that multi-layer perceptron? We just saw deep learning. So, according to trends, when I look at recent papers, it's more and more common to call these multi-layer perceptrons deep learning. So, here's just a figure I saw recently in a paper here. Um, that are read. For example, there was this figure of a multi-layer perceptron where there were only 10 inputs, very small number of hidden units, and then one output. So this is the output unit. So here they call it deep learning, and essentially propose this deep survival model. So like I said, it's more and more common to call these multi-layer perceptrons deep learning. Traditionally, when the term deep learning was coined, it usually referred to the feature learning by using certain tricks that are a little bit about beyond the regular multilayer perceptrons, where we had certain algorithmic improvements of neural networks that make the learning more efficient. But nowadays, multilayer perceptrons, I would say, is already deep learning in a sense. Now, another very important point is that now in multilayer perceptron, the loss is not convex anymore. So, linear regression, Adeline, logistic regression, and softmax regression, we had convex loss function. For example, for linear regression, if we recap how the loss looked like, let's say with respect to one weight, because it's easier to draw, it would be something like this bowl shape here, where let's say we start with an arbitrary weight value. Let's say we start with weight 0, so the loss would be very high when we start, and then we go down with the gradient descent till we reach this global minimum. Now, in this case, in the case of multi-layer perceptrons, it's not that simple anymore. We don't have such a nice convex loss function where there is only a path downward to the global minimum. So in fact, these are highly non-convex loss surfaces now. So I found a nice paper that is about visualizing the loss landscapes of neural networks. So here, if you have our consider two weights in a neural network. So if we have, let's say, W1 and W2, let's say W11 and W12, W21, and let's say in the first hidden layer, because there are many weights in the neural networks, but you can see that this loss is highly complex. There are many local minima going on here, and here I think this that should be the global minimum. So if I find the value of weights that we are here at this point for this loss, so here the loss value, let's say the higher, this is the maximum, the higher the loss, the higher or larger the loss, and the lower will be the lower the loss. So lower value means lower the loss. So if we add this global minimum here, then we would have minimized the loss function with respect to the weights. However, depending on what our starting weights are, so typically in the context of neural network training, we start with small round random weights. So one reason why we start with small random weights is that we want to try different configurations. So for example, if we have a configuration of weights, we may start here. We could start here or here, wherever, depending on what our initial weights are. And it's not uncommon that we get stuck in the local minimum. So we reach one of these local minima and then the algorithm gets stuck. In practice, it's actually almost, I would say, impossible to find the global minimum. So you never know whether you reach the global minimum. Usually, common knowledge is that you will end up in some of the local minima, and it's not uncommon that because of that, to start the neural network training multiple times with different random sets, random seeds. So sometimes you have a better random seed for a given network than the others, other times. So sometimes you will notice that you will have a better performance just by changing the random seed. So in papers, it's almost also not uncommon to, let's say, run a network training for 5 or 10 times, then take maybe the best 3 runs and then average over them and report the standard deviation and things like that. So we deal now with this highly non-convex loss surface, and in the next couple of videos we will also talk about tricks for learning rates, choosing initial weights, and choosing optimization algorithms that can help jumping out of these local minima once we get stuck. So there are certain tricks and improvements to make the learning rate more efficient compared to the traditional stochastic gradient descent version. Now, beyond choosing good starting weights and good learning rates and good optimizers, it's also very important to choose good activation functions and combinations of activation and loss functions. So here I just wanted to illustrate a problem with certain activation and loss functions. And in the next videos, we will talk about, let's say, alternative activation functions, which are nowadays a little bit better for training multi-layer perceptrons. So here for this example, consider we have a logistic sigmoid activation and the mean squared error loss function. So one problem we may encounter is that we may end up with very flat gradients, and especially then if the output is very wrong. But if you think about it, if we make a very wrong prediction, we want to actually have a large gradient, because then we can update the weights more. If the gradients are very flat, then there's almost zero weight update, and then we can fix our problem of wrong predictions. So recall how the logistic sigmoid function looked like. So if you have a logistic sigmoid function like this with a net input, then recall it was like a S-shaped function, and let's say the true class label is 1, but we return a very low probability, like let's say the probability class membership is 0.001 or something like that. So if you look at this figure, a low, very negative net input is a low probability will result, of course, in these very flat gradients. So if you then look at the derivative of this loss function with respect to the weights, so here we have the derivatives of mean squared error loss with respect to, let's say, the activation, and then this is partial derivative of sigma with respect to the net input, and then the last term is the derivative of the net input with respect to the weights. So here we again use chain rule, but if we have these, the derivative of sigmoid here, and now we see the combined with these MSE doesn't cancel so nicely. So when we had the binary cross entropy and the sigmoid activation, things cancelled nicely, that we ended up with this nice learning rule. But if we use, for example, a mean squared error function like we are doing right now, combined with the sigmoid activations, we end up with this derivative here that has the problem that it has uh, this term itself. Now if this term is very small, so if we make a very wrong prediction, let's say probability is 0.0001, maybe even smaller, let's say 0.00001 or even smaller, then we multiply this very small value with all the other values here, so the whole derivative will become very low or very small, and then we will almost update our weights by nothing. So in that way we can fix this wrong prediction. So it's kind of also important to think a little bit about what type of activation functions we combine with which type of loss functions. Here's another point, but here this point what it really means is if you have a multi-layer network, of course, you would use a softmax activation if you have a mutually exclusive classes instead of sigmoid activation in the last layer, but the same problem would still exist. So that doesn't really solve all the problems. Alright, so in the next video, I will show you then different types of activation functions that are a little bit better than logistic sigmoid function in the multi-layer perceptron. And that's it for this video. If you have any questions, drop them in the comment box below, and I'll see you in the next video.